All right, today we are going to cover 7.2, which is properties of graphs of quadratic functions. So, to start things off, we are going to think back of standard form of a quadratic function, which we introduced the other day, which is y is equal to ax squared plus bx plus c. Okay, so our a, b, and c values could be any real numbers except a can't equal to 0. What we are going to do is we're going to introduce a whack ton of terms today. It's going to be great because you're going to be so smart afterwards. And we're going to then use all of these definitions that we introduce to kind of talk about different graphs of a quadratic. So to kick things off, we have the vertex. And the vertex is the point at which the quadratic function changes direction. So the vertex can also be thought of as the maximum or minimum value. The vertex is the maximum or minimum value. So the vertex is the point at which the quadratic function changes direction, which means the graph was going up, 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 and all of a sudden it's going down, 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 down. Or it was going down, 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 and all of a sudden it goes up, 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 up. It's that point in which we have a change of direction. You could also call it a turning point. Okay. The maximum value is the greatest value of the dependent variable. Greatest value of the dependent variable. And we know that our dependent variable is always on our y-axis. So it's going to be our greatest y value. Similarly, the minimum value is the lowest value of the dependent variable. So the lowest value of the dependent variable, which again is our y value. So our vertex is going to represent either our maximum or our minimum, and that is always going to be based on the maximum or minimum value of our dependent or y variable. So we're going to look at a couple of different examples below. For each quadratic function, we're going to label the vertex and determine whether it's a maximum or a minimum. So the vertex occurs on this first graph right over here, because as you can see, if I read my graph from left to right, it's increasing, 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 stop, decreasing, 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 decreasing. And that point in which it changes direction is that vertex. And my vertex occurs at the point 2, 4. Okay, because we have 2 on the x-axis, 4 on the y-axis, so my vertex is 2, 4. In this case, my vertex represents a maximum, right? Because in terms of the y value, that is the highest point it reaches, and it doesn't go any higher than that. So we could say my maximum occurs at my point y is equal to 4. Right? So my maximum y value is 4. On our next graph here, our vertex is located over here at the point 2, 3. 2, 3. But in this case, it's a minimum, right? Because it's going down, 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 stop, up, 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 up. Right? So it's that change in direction point. Here we have a minimum. And that happens when my y value is positive 3. Okay? So something to keep in mind is that our minimum or maximums will always occur at the y value of our vertex. All right. Next, we have an axis of symmetry. So what an axis of symmetry is, it's an imaginary line. It's not something that's actually graphed, but something that we could picture. Imaginary vertical line, I should say, that divides the graph into two equal halves. The axis of symmetry always passes through the vertex. Always passes through the vertex of our graph, and we know that graph is called a parabola, so the vertex of the parabola. And it will have the equation x is equal to whatever the x coordinate is of my vertex. Okay. So this here is pretty important because usually when asked what the axis of symmetry is, we want to give the equation of that line. Because it is a vertical line that passes through the vertex, a vertical line on the graph will always be represented by x is equal to some constant, some number. And that number can actually be that x coordinate of the vertex. So if we're looking at the graphs below, first of all, we're going to start off by labeling the vertex. So here we have the vertex, and it's on the point 2, 6. And you'll notice in this question here, we have the axis of symmetry as this dashed line. This axis of symmetry doesn't actually exist, it's imaginary. But just for the sake of showing you, like, hey, this is where the axis of symmetry is, you could fold that paper in half on that line, and we will have two equal sides of that parabola. But that axis of symmetry doesn't actually exist in real life. But when we're trying to find out the equation of that axis of symmetry for that vertical line, it's x equal to whatever the x coordinate is of my graph, or I'm sorry, of my vertex, which is 2. So I'll have x is equal to 2 is the equation of my axis of symmetry. Okay. The next one here, we're going to start by labeling the vertex. And the vertex is the point -6, -4. -6, whoops, sorry about that. Where am I now? Stop. Ay. What did I do? Dang. Let's try closing this and reopening it. Alright, that seemed to work. And we are moving downwards. Yes. Alright, so the vertex here is at -6, -4. And my axis of symmetry, again, is on that dashed line that we see down the middle here. Again, that line is not something that will show up when you graph it yourself or something that you graph on Desmos, but does in fact exist. Let me just turn off the Wi-Fi here. Maybe that'll help. All right, so my axis of symmetry is going to be x is equal to -6. All right. Next, we are going to be talking about x-intercepts, and we've talked about x-intercepts before, but just to kind of give a formal definition to it, the x-intercepts are the coordinate, or the x-coordinate, of a point where the graph touches or intersects the x-axis. Right, so I say touches as in as long as it touches it, that is considered an x-intercept. It doesn't have to go right through. Big thing here is that these occur when y is equal to 0. Okay, big thing. We could also talk about x-intercepts depending on the context that we're using. They're also known as zeros or roots. We often say they're called roots when we're talking about solving by factoring. And we also usually call them zeros when we're talking about a graph or something like that, or if we're talking about solutions, if we set an equation equal to 0. So we kind of choose what we call them depending on the context that we're given, but those are some common names that kind of refer to the same points. Okay, so the example here says, how many x-intercepts does each quadratic function have, and what are they? So for starters here, we have 2 x-intercepts in this first graph. So you have 2 x-intercepts. And the first one occurs when x is equal to -3, or we could say -3, 0, because that is the coordinate point for it, right? Because our y is equal to 0 whenever we have an x-intercept. Or we could say x is equal to +7 or 7, 0, because we have 2 x-intercepts. In this middle graph, we have exactly 1 x-intercept. And that occurs at the origin when x is equal to 0, or the point 0, 0. In the last graph, we have 0 x-intercepts. Oops, I don't need that dash there. So we could say that they do not exist, DNE. We cannot write x is equal to 0 because we have 0 x-intercepts, because realistically an x-intercept can occur when x is equal to 0. So that would be incorrect. Writing DNE, that represents the slogan or the saying does not exist, because our x-intercepts do not exist at this particular graph. Alrighty. Next, we're going to be talking about y-intercepts. So the y-intercept is the y-coordinate of a point when the graph touches or intersects the y-axis. And key point is this occurs when x is equal to 0. Okay. So just like our x-intercepts occur when y is equal to 0, our y-intercepts occur when x is equal to 0. So looking at these quadratic functions below, we want to figure out how many y-intercepts each has and what they are. So for this first guy here, we have exactly 1 y-intercept. And that occurs when y is equal to 4, or at the coordinate point 0, 4. And we could say 0, 4 because 0 is the x-coordinate when y is equal to 4. But we know x is equal to be 0 because that is something that's always true for y-intercepts. This next graph here, same idea. It will also have 1 y-intercept. And that occurs when y is equal to 12. Or at the coordinate point 0, 12. Because x is always 0 when we have a y-intercept. Alrighty. What we're going to do next is we're going to review interval notation and set notation just a little bit we're going to do a quick reminder of what those symbols mean that we use in each of the different notations. We're going to practice using the different notation for a couple of graphs. Whenever we do any questions in this unit where I ask you to show me or explain to me what the domain or range is, I actually don't mind which notation you use. You could use interval notation, you could use set notation, it doesn't quite matter. Same with grade 12 applied. When we go ahead and we talk about domain and range, you could use either or, but you do need to be able to read either. So sometimes I could give you a question that has something in interval notation or set notation and say, hey, is this correct? Yes or no. Yes or no. And you should be able to understand what that means. Okay, so we're going to go through what they are. We're going to explain all of the different notation, but you can choose which you use when you go through and do your own questions. So, kick things off. Interval notation. It is a way of writing subsets of a real number line. Interval notation uses brackets to denote the interval of numbers included. Okay, so interval notation is a way of writing subsets of a real number line. Interval notation uses brackets to denote the interval of numbers included. So we have soft brackets, and that implies that the interval does not include that value. And we always use it with infinity, because infinity itself cannot be included. You could get close to infinity, but you can never catch it. So we always use soft brackets when we're talking about infinity. We also have these brackets here that we call square brackets, or sometimes we refer to them as hard brackets. And these imply the interval does include that value. Okay? So interval notation, we have soft brackets or we have square brackets. Please make sure when you're using them it's quite obvious which ones you are showing. But the soft brackets imply that the value is not included, or we are using something like infinity, where square brackets implies that that value is in fact included in that interval. We also have set notation, and set notation is a way of writing subsets of any number line. So you might have noticed in interval notation it talks about any real number line, whereas set notation is any number line, because we can have a number line of integers, we can have a number line of whole numbers, all of the above. So set notation is a little bit more inclusive of what you can use it for, but in this unit you could use either. Both will always include real numbers. Okay. Set notation uses inequalities and symbols to denote the numbers included. So there's a variety of different symbols that set notation uses. I'm going to introduce all of the symbols, which hopefully you remember a little bit from last year. And then we are going to go ahead and jump into an example using both interval and set notation. So the first symbol that you should be aware of are these squiggly brackets. They mean the set of. So with set notation, we read all of these symbols like English words, and it should make a beautiful sentence. So the next symbols that we have are the letter X or the letter Y. It's not X/Y or X divided by Y. It's just we could use one or the other. And that usually refers to all X or all Y, depending what we're talking about. The next symbol we have is this vertical line. It represents the words such that. Then we have different inequalities. So we could use either of these depending on what the situation implies. So we could have less than or equal to, greater than or equal to, greater than. So these are just different types of inequalities. And hopefully, after our last unit, we feel pretty comfortable with inequalities. Then the next kind of symbol that we might see is this guy here. It's kind of like a C with a line in the middle of it, or a really soft capital E. And that means is an element of. And the last symbols that we might see are our number set symbols. So we can have this double-lined R, this double-lined W, this double-lined N, or this double-lined Z. And they refer to different number sets. So double-lined R is the real numbers. Double-lined W is whole numbers. Double-lined N is the natural numbers. And double-lined Z is our integers. Okay. So mostly in this unit we'll be talking about the real numbers. And that's why we can use interval notation as well, because it applies to any real number line. But down the road you might see whole numbers, natural numbers, or integers used, so that's important to know. Alrighty, so we're going to jump right into it, and we're going to look at this this graph here, and we're going to try and indicate our domain and our range of both, or in both notations. Okay, so for interval notation, for our domain reminder talks about all values of our x-axis, so what is furthest left to what is furthest right. And as we could see in our graph, it continues in both directions. So it continues all the way down to negative infinity and continues all the way up to positive infinity. So for our interval notation, we always go our smallest value first, negative infinity, all the way to our largest value. And since we are using infinity, we always use soft brackets with infinity because we cannot include the value itself. Since we cannot include the value itself, we use soft brackets. For set notation, what we do is we use those symbols that we introduced above and create a math sentence. So set notation will always start with the set of, and then the variable that we're talking about. In this case, since we're talking about domain, we're talking about x. So the set of all x such that. We are not including any inequalities in this particular case because there are no additional restrictions on x, right? It's not like x has to be less than 0 or greater than or equal to 5, right? There's no restrictions that we have to add in. But x itself is an element of the real numbers, which means it can take on any value in the real numbers. It could take on negative 547. It could take on positive 2.31111184. Right? So our x could take on any value. So the way that we read it is we go the set of all x such that x is an element of the real numbers. So we go ahead and reread that across as a full math sentence. All right, for our range we always talk about our y values, and we always talk about from the bottom up. So I always think of it as like started from the bottom, now we're here, or bottoms up, however you prefer. And so we're looking at our y value, and the smallest value of our y occurs at our minimum, right? And our minimum here occurs at our vertex. And our minimum value is when y is equal to 3. So we have 3 as our smallest, and we can see that it continues up in either direction all the way on forever and ever and ever. So we go up until infinity. And with our 3, there is a physical point at our vertex that exists on our graph. So we use our hard or square brackets to include that 3 in our interval. But with infinity, we always use soft brackets. If we wanted to write this in set notation, we start off in kind of the same way as before, in the sense that we always have the set of the variable that we're talking about. In this case, since it's range, we're talking about y, and such that. Here we do, in fact, have some restrictions, right? In this case, y could be any value that is equal to 3 or greater than 3. So we go y is greater than or equal to 3, and then y could take on any value of the real numbers. So the way that we read that is the set of all y such that y is greater than or equal to 3 and y is an element of the real numbers. So as we're reading across our set notation, it should again read like a math sentence. So the symbols are used so that they replace words, so we don't have to write this long sentence, but just to write the short little statement that reads like a sentence. Okay? All right, so those are all of the characteristics that we are going to introduce in this lesson. From the rest of this, we are just going to go and identify some points of our graph. So we could be given a graph or just a photo of a graph so that we could analyze some of the things. And we're going to go ahead and do that now. So the first thing that it asks us to find is that vertex. And our vertex occurs right there. And we can see that occurs at the point -4, comma, -9. -4, -9. Our axis of symmetry, although it is invisible, we know that goes right through our vertex there. So if we folded that paper across that axis of symmetry, we'd have 2 equal halves. And we have to write the equation of an axis of symmetry as a vertical line. So x is equal to -4. Because remember, we use that x coordinate from our vertex as our axis of symmetry. For x-intercepts, we have one over here and we have one over there. So we could say we have x is equal to -10, or we can write it as the point -10, 0. And we have x is equal to +2, or we could write it as the point 2, 0. Again, both of those are equal or equally acceptable ways for you to indicate your final answer. Choose whichever you like. For our y-intercept, we have our y-intercept occurring over here. Y is equal to our -5, or at the point 0, -5. Again, both are acceptable. Our domain, in this case, that is all of our x values from left to right. If we want to write them as interval notation, they extend all the way from -infinity to +infinity. If we want to write it in set notation, we have the set of all x such that x is an element of the real numbers. For our range, we have a minimum again for our y. That minimum value is our -9. We can see that on our vertex, right? When we talked about minimums and maximums, that's always occur at our vertex. Since -9 is in fact included, we use a square bracket, and our range extends all the way to infinity. If we wanted to write that in set notation, we would have the set of all y such that y is greater than or equal to -9, and y is an element of the real numbers. All right, there is one more that's essentially identical in the process that we take. What I'd like you to do is pause the video at this moment, try it out on your own, and then resume the video once you're done to double check to make sure your answers are on the same page as mine. Pause now. And welcome back. All right, so we are going to go through these together. So we have our vertex occurring right over here. That happens at the point -4, +2. Our axis of symmetry, again, passes through the vertex. This is vertical line right through. And so that happens at x is equal to -4. We have two x-intercepts again, so x is equal to -6, or the point -6, 0. And x is equal to -2, or the point -2, 0. We have one y-intercept, and our y-intercept occurs at y is equal to -6, or 0, -6, because x is always 0 when we have a y-intercept. Our domain, in interval notation, the smallest value to the left is -infinity. It extends all the way to +infinity. We use soft brackets for infinity. Or in set notation, we go the set of all x such that x is an element of the reals. For our range, we always go bottoms up, so the smallest value it takes on is -infinity, and it stops at a maximum point, and that maximum occurs at 2. And since 2 is included, there's a physical point there, we use a hard or square bracket. In set notation, we would write the set of all y's such that y is actually going to be less than or equal to 2, and y is an element of the real numbers. Alrighty. So, in this unit, we will also be using Desmos. If we were in class, I would be asking you to download the Desmos Test Mode app. The Test Mode app allows us to do assessments together where it prevents you from using other apps or screens or getting any sort of notifications from it. At this point, because the notes that we're doing in class, you could also work with just the regular Desmos app. The Desmos Test Mode app doesn't quite work for Androids the same yet, but it does work for iPhones just fine. But the Desmos itself app looks like this green kind of squiggly graphing thing at the bottom here. With that being said, I'm going to open up Desmos because we're going to be using it together. So when you go ahead and continue with the rest of this unit, it is going to be useful for you to use the Desmos app. The Desmos can also be opened on your internet browser as desmos.com, and then you'll be able to use it that way as well if you prefer that kind of view screen. But it is something that you could have on your device that's handy and with you at all times. All right, so we're going to be using the Desmos app to start graphing some things and to analyze some of the points on it. So here we have the quadratic function y is equal to x squared minus 2x minus 3. To plug that into Desmos, we write it out exactly as we see it. So y is equal to y is equal to x squared minus 2x minus 3. And this is the graph that we get here. And you'll notice we have some key points that will help us to graph it in the same way. So here I'm going to make sure that my axes are labeled so that I know which one's which. But I'm going to go ahead and start plotting these points. So I have -1, 0. I have 0, -3. I have 1, -4, and I have 3, 0. Something to keep in mind is that 1, -4 is my vertex. So I'm going to have an axis of symmetry here. If I have an axis of symmetry there, that means if I fold my paper along the axis of symmetry, I'm going to get the exact same 2 halves right directly on top of each other. The reason that I bring that up is that if I have a point here that is 1 away from my axis of symmetry, I will also have a point here that's 1 away from my axis of symmetry. So even though I don't have that popping up as a very obvious point on my graph, I could show you here, if I put x is equal to 2, I could show you that that point on my graph is 2, -3, which is exactly what we drew there as well. Okay. You'll notice that that graph kind of continues on forever on Desmos, and just to help us better draw things, I know we have some points for -1, 0, 1, 2, 3, but if we could continue at some point along when x is equal to -2 and x is equal to +4, that might help us draw this graph out a little bit more nicely. So in my Desmos, I could put x is equal to -2. And I could find that intersection there that occurs at the point -2, 5. And I can draw that point in here. I can use my axis of symmetry and say, well, if I have a point that's 3 over this way, I should have a point that's 3 over that way as well. And to double check that I'm right, well, let's see what happens when x is equal to +4. I also have the point 4, 5. So that's kind of neat. So if we end up having some points on our graph, we can always find more as long as it's not on the vertex by using the axis of symmetry. So that's kind of cool. We can extend or connect these dots as best as we can by drawing a nice smooth curve through it all. And arrows on the edge here because Desmos would continue on forever. We don't have the time for that or the patience. And even if we did, we would continue on forever and just our whole life would be dedicated to finishing that graph. But instead, we could just draw arrows to indicate that. It makes life a little bit easier. And I can do that to both sides. So my graph should roughly resemble what I have on Desmos. Okay. All right. From here, close Desmos down a little bit, I could go ahead and answer what I have for these different points. So my vertex occurs at the point 1, -4. My axis of symmetry occurs when x is equal to 1. I have 2 x-intercepts, one where x is equal to -1, or the point -1, 0. And the other one when x is equal to +3, or the point 3, 0. I have 1 y-intercept, and that occurs when y is equal to -3, or the point 0, -3. My domain from left to right, smallest value left, is -infinity to +infinity. Or my set notation is my set of all x, such that x is an element of the reals. And my range has a minimum. So my minimum value is -4, so I use a hard bracket with that. And it goes all the way into infinity, which I use a soft bracket. And in set notation, I could say the set of all y such that y is greater than or equal to -4, and y is an element of the reals. So essentially, all we did that was different is that we copied down the image of the graph from Desmos, and then we were able to analyze our information from that. So it shouldn't be too much of a change. All right, we have one more page left in today's notes before our homework. We are going to do the first one together, but after the first one, feel free to pause and go ahead and try the rest on your own. Okay? open up Desmos a little bit more here. What we're going to do is we're going to graph that equation here. So we have y is equal to negative x squared plus 4x minus 3. And we're going to look at this graph, and we could actually get all of the information that we need straight from it. So here, this is kind of what our graph looks like. We can see that there is a maximum that we have. But from our graph on Desmos, we can just go ahead and click on those points that pop up and figure out all of the key information. So our vertex occurs at the point 2, 1, which means our axis of symmetry is that vertical line that goes right through that vertex, which is at x is equal to 2. That is the equation of a vertical line. We have two x-intercepts. One occurs at x is equal to 0, one occurs at x equals 3. So, or sorry, not x is equal to 0. X is equal to 1 and x is equal to 3. So x is equal to 1, and so we could either write that as a coordinate point 1, 0, and x is equal to 3, and we could write that as a coordinate point 3, 0. We have a y-intercept, and the y-intercept occurs when y is equal to negative 3, or at the point 0, negative 3. Our domain, again, we could zoom out, scroll down, do all that jazz, but notice that our domain goes from negative infinity to positive infinity, or as in set notation, x is, or the set of all x such that x is an element of the reals. And our range is, we have a maximum, so negative infinity all the way to our maximum of positive 1 that we use a hard bracket for. And in set notation, we have the set of all y such that y is less than or equal to 1, and y is an element of the reals. All right, at this point, what I want you to do is I want you to pause the video. I want you to finish the last two on your own, and then you could come back and double check all of your answers to make sure that you are on the right track. But at this point, you should be able to feel pretty confident to get some of this done on your own. So pause the video now. Alrighty, welcome back. We are going to do the last two, and we're going to do them fairly quickly because at this point you're just checking your answers. So we're plugging in the equation that we're given. Make sure that it looks exactly like what we have on our sheet of paper. So y is equal to 1/2 x squared minus 3x plus 4. We have the vertex at 3, negative 0.5. So 3, negative 0.5. Having decimals or fractions are more than okay. Life is good either way. Our axis of symmetry is that vertical line that passes through it. So we have x is equal to positive 3. In this case, we have two x-intercepts. The x-intercepts occur at x is equal to 2 and x is equal to 4. So x is equal to 2 or the point 2, 0, and x is equal to 4 or the point 4, 0. We have a y-intercept when y is equal to 4, or you could say at the point 0, 4. Our domain, again, from left to right, is negative infinity to positive infinity, or the set of all x such that x is an element of the reals. And our range, we have a minimum this time. So we have our smallest value of y as negative 0.5 and all the way to positive infinity. In set notation, we could say the set of all y such that y is greater than or equal to negative 0.5. Y is an element of the reals. And remember that we can get our minimum value from our vertex. All right, last but not least. So our last one is 2x squared minus 10x plus 9. 2x squared minus 10x plus 9, perfect. And we can go ahead and get all of this information. And I realize that some of this information has lots of decimals. So that is a-okay. Decimals don't freak us out. Life is still muy buen. Muy bien? I don't know. So here we have another minimum. Our vertex occurs at, oops, I don't want to highlighter, at 2.5 comma negative 3.5. Our axis of symmetry is a vertical line that extends right through that vertex. So when we have x is equal to 2.5 as our axis of symmetry, we have two x-intercepts. The first one occurs when x is equal to 1.177 or the point 1.177 comma 0. The second one occurs when x is equal to 3.823, or the point 3.823 comma 0. Both represent the same thing. Our y-intercept occurs exactly when y is equal to 9, or the point 0 comma 9. Our domain, same as before, it extends from negative infinity to positive infinity, or the set of all x such that x is an element of the reals. And our range goes from this minimum point of negative 3.5 all the way to infinity, or the set of all y such that y is greater than or equal to negative 3.5, and y is an element of the reals. Alrighty, that is it for today. You have some homework that follows. You are more than able to use your Desmos app for any part through anything in this unit. It is not cheating. It is a tool that you can use for your own success. Please use that to the best of your abilities. Otherwise, that is all for today. Peace out, homies.